So, are there any questions from previous lectures? Okay, so I will just be talking about the streaming now, and let me just restrict to the left moving sector. So in a flat background, the action is quadratic. Okay, and if you're doing heterotic, then the right moving sector is like the RNS heterotic sector. If you're doing type 2, type 2b, then these are the same chirality. If you're doing type 2a, these are the opposite chirality. Similarly for the ghosts. Okay, so this needs to be augmented by the RST operator. So this d alpha is of course constructed out of p and dx. But you need an additional term, so this plays the role of capital P, but you need an additional term in order that the d alpha is space-time supersymmetric. So the additional term is and I may be wrong with signs. So this object actually was first constructed by Siegel, and it satisfies the following OPEs. So of course the OPE of P and theta is just free field OPEs. And of course dx with dx, or x with dx.
You are saying that this doesn't reduce to the point particle one.
That's right. So if we restrict to just, if we take the alpha prime and go into zero limits, or we just assume the fields are independent of sigma, then this just gives me x dot squared sp theta dot plus w lambda. So that's what we had for the part. Okay, so using these, the other one you need is the ends, so that Carlos already wrote down for you, and n with n. And this, as I'll show in a second, it goes like -3. So this goes like gamma and n. And NMN is the Lorentz curve. Okay. Just before I prove this -3, let me just finish what I was saying here. So using these OPEs, one finds that d with t goes like pi m where pi m so it's the space-time supersymmetric version of dx. So one more thing I can say is that the action can be written it manifests a space-time supersymmetric form, if you like. Now it depends a little bit about if we're doing type 2 or type or heterotic, but let me just write a B field, and I'll tell you what that is in a second. So this B is the same as in Green-Schwarz. So it's constructed out of the x and thetas in such a way that it's space-time supersymmetric up to total derivatives. And if you just had this action here, it would be invariant under kappa symmetry. So, if you want to write this action in space-time supersymmetric form, you can say it's equal to Green-Schwarz up to terms which involve these d's. So of course, if you set d to 0, you just get back to the Green-Schwarz act, if you ignore the ghosts.
So in both the terms there, y minus a, one will be 1 minus it.
I'm sorry, can you repeat the question?
Operator product expression of in and in, both. How will 1 minus a?
Oh, so this should be,
So these two actions are not the same, right?
this action is equal to the action of. So let me explain how to show it. So of course pi m has other terms in it. D alpha has other terms in it. But if you take all these other terms, well, the other terms means this one and this one and this one, and plug them in here, they're exactly cancelled by the B.
Expression for d alpha, what is the second term, del del theta?
I'm not sure about the sign, but it's 1/8 gamma m theta, theta gamma m.
Second term.
Oh, the second term is dx slash theta.
Ah, okay.
Any other question? So of course space
Can
time.
you go from where do you use the n OP when you get the d alpha d beta OP?
Where? How did I drive this?
No, you need to use n because there is
No.
no n.
No, no.
You didn't use n.
So in fact, this OPE was already found by Seagulls. So what he did was he just said, well, d alpha are the constraints of Green-Schwarz. Let me write just Green-Schwarz in first order form. So let's just add this term. And just let's compute the OPEs. And he found it. Now there's a few more OPEs that will be useful, which is d alpha with pi m. So of course these two objects are space-time supersymmetric, so the OPE also is space-time supersymmetric. It's not hard to show that it's gamma m alpha beta d beta beta over 1 minus.
So this will be your starting action now, is that right?
Either this one or that one, yeah, they're both equal.
Both equal, right?
So of course, it's easier for me to work with the quadratic one. But I just wrote this one so you can understand the relation with the usual Green-Schwarz. But again,
What is B? Did you define B sometime?
okay, so B is like in Green-Schwarz. So it depends if you're doing heterotic or you're doing type 2. So for heterotic, this is equal to dxn theta in minus, again, up to factors of a half. So it's antisymmetric in D and D bar. Now, if you're doing type 2, you also, of course, involve the theta halves, and you also have a term which is quartic in the thetas. But this is precisely the same. The reason why it's called B is because when you do this in a curved background, It turns out that B is equal to BMN. Let me call it Z. Where Zn is equal to Xn or beta alpha or beta alpha. So if you're working in a curved background, you can of course have a antisymmetric tensor field. So the vector indices of these are just the usual BMN field. You have a short sector. When you work in superspace, these vector indices can either be vectors or spinors, just like we had A alpha and AM for the Yang-Mills gauge fields. But also, all of the background fields can either be vector or spinor indices. And it turns out in a flat background, although the B with vector indices is 0, the B with spinor indices is not 0. So the one with one spinor and one vector index is not 0, and that generates this term here.
This is superspace torsion.
So this is superspace. So this is in flat background, B is not 0.
It's a torsion of the superspaces. Is it or no?
Yes, it's related to the torsion. That's right. Okay, any other questions?
So this D hat alpha, those are the first class one.
D alpha, so if you just, I'm sorry?
Hat alpha.
The hat means the right moving.
Right.
These are the left moving, these are the right moving. Any other questions?
In heterotic, you will just omit the hats.
In the heterotic, that's right, we would replace this with the usual B bar, C bar of heterotic string. Plus you would have the size, or whatever you want, what letter you use for the fermions. So you have something like CJ, D bar, or D equals CJ, for the right moving fermion. Okay, any other questions?
In the action, alpha prime is overall factor, there is some relative.
Yeah, there's always 1 over 2 pi alpha prime. So, the only term this is important for is for these two terms. For these two terms, actually, you can often rescale alpha prime away just by rescaling D or W. But for the x-dependent terms, there's always an overlap. But I'm going to set alpha prime to whatever to cancel out.
And in this formulation, you don't even have the usual B, C.
Right, that's what I'm going to discuss. That's right. So it's conformally invariant without this SPC. Any more questions?
So you said alpha prime can be absorbed in the other terms, D and
Yeah.
W.
For these terms, it's ambiguous. I mean, you can, by rescaling D and W, you can get rid of alpha prime if you like. It's just because the tension is really related to X, not with fermionic variant. So then, of course, we'll shuffle the alpha primes around here. But
Oh, so
okay, so space-time supersymmetry just shifts theta, shifts x by epsilon gamma theta, but it also shifts p. Okay, so I'm not going to write it down, but it leaves d alpha invariant. Okay, so the thing that I now want to show you is this -3. So there's a very simple way to get it, which is by expanding NMM in terms of the unconstrained field. So you remember that lambda alpha, I could write in terms of gamma, gamma u d, and epsilon a, b, c, d, e, u, b, c, u, d, e over gamma. And similarly, that assuming that this component of lambda is non-zero, you can gauge away 5 components of W, and the other ones I can just call, the other one is VAB, and And then there's something that's proportional to V, U, U, and the final components are 0. So this is A down. I probably should have done it the other way. It's 0, V, A, B, so this is supposed to be conjugate to this is the conjugate to this. Oh, I forgot one component.
What is
Saying
what about written on the part? In omega, what is this?
I said it wrong. Let me try to say it again. So we're writing the conjugate momentum to lambda. Now, if gamma is non-zero, remember there's a gauge invariance of W, which allows me to gauge 5 of the components to 0. So, as I said before, just erase. So these 5 components are 0. These 10 components are the conjugates to U, and beta is the conjugate to gamma. So if I wrote this action W d lambda in terms of the unconstrained field, it would just be E squared Z UAB plus VAB d bar UAB plus beta d bar gamma. Now, if I look at NMN is equal to W and in order to compute this level, I don't have to know all the n's, I just have to know 2 of the n's and just check what the level is. So it's convenient to just look at NAB. So A goes from 1 to 5, remember. So this is in the U5 subgroup of SO10. Because 1 5 index up, 1 5 index down. Now it's easy to see if it's in SU5 and not U5, this is just equal to VAB, VAC, UCB. And these are the only fields that transform under the SU5, so obviously it's just built out of the V's and U's. It doesn't involve the betas or gammas.
So you are using this gauge.
I'm using this gauge. So I can compute it in any gauge because this is a Lorentz covariance. Okay, now we can just look at one of these elements. So let's look at N12. So this has 3 terms, V13, U32, plus V14, U42, plus V15, U52. And now it's clear, if you take N12 with N21, you'll get 3 contributions, 3 double poles. One, this one was one from here, one. So you get, using the fact that these are bosonic, you find that it gives you -3. So the -3 just comes from here. Okay, so that's the simplest way to get this -3. Of course, there are more complicated ways to get it. So in general, if you're working in d dimensions, it's always going to be, for pure spin, it's going to be d over 2 minus 2.
So the sig minus W or 1 minus sig term will come from, it should be UV or UU.
You're saying, why is there a minus sign? Is that the question?
What is the minus sign? This expansion in Y and Z. That
Yes.
will come from the UU OPs or?
So because they're bosonic, V with U goes like 1 over 1 minus Z, but U with V goes like minus 1 over 1 minus Z. So that means when you contract this with U and V, you get a minus sign from here and a plus sign from here. So if they were fermionic, then you would have plus, because they're bosonic. Okay, so that's this level that I mentioned yesterday, or Tuesday, is necessary in order for the Lorentz currents to have the same level as in RNS. So that's, in some sense, an independent way to see why pure spinors. Essentially, the sum of a pure spinor, a bosonic pure spinor, and a fermionic ordinary spinor is a fermionic vector. And so, you have, in some sense, P theta okay, plus quotations from the lambda, this is equal quotations again, of course. Sorry. At least the levels of the Lorentz curve. Okay, so that's what I wanted to say about these OPEs, and now we want to use these OPEs to compute scattering amplitude. Okay. Now, Carlos already mentioned the integrated vertex operator. So this written in terms of these superfields that Carlos already defined for you. This W is the lowest component of W is the gluino, and the lowest component of F is the field strength of the gluon. And as he said, it satisfies the property that QU is equal to the derivative of D. So to show that, we have to use the fact in these OPEs that Q on theta is obviously lambda alpha. Q on IM using this OPE here is equal to lambda gamma MD theta. Q on D alpha, now using this OPE, is equal to pi slash lambda. And Q on NMN is equal to lambda gamma MD. So these are the properties we will need, for example, to show that Q of U is equal to dV.
Can one show that these are the same homology as RNS?
Yes, so the simplest way to do it is to construct DDF operators. So one writes Q. So, of course, there's no simple way to do it covariantly. So what one can show is that there's a gauge for the vertex operators in which they're analogous to the light cone vertex operators in Green-Schwarz, which are of course analogous to the light cone vertex operators in RNS. So it's not so complicated to do. It was done together with Renan Jusinskas, I think 2 or 3 years ago. You write Q in terms of a simpler object. It's similar, not so different from what people do in bosonic string theory to construct DDF operators. So you find a similarity transformation which simplifies Q. This is not Lorentz covariant, it's similarity transformation. And the similarity transformation, after doing it, Q hat has the form of something that allows you to say that the fields are independent of, for example, x plus and x minus and half of the thetas, and they form that they only depend on the light cone Green-Schwarz degree of freedom. So, if people are interested, tomorrow I can tell you what this is, but I don't remember it right offhand. Okay, so the proof of that you get the right spectrum is now complete. I mean, in the original argument, it was just, well, it was easy to show that the massless sector has the right spectrum. And then you can argue that the massive states are all obtained by OPs of the massless states. Or if you like the poles and the scattering amplitudes, the fact that you get the 4-point amplitude correct tells you that the intermediate states are also correct. But, okay, to do it concretely, you have to just construct the vertex operators and show that those are the states in the cohomology, and that can be done not in a covariant way, but using this DDF procedure. So what is R? Okay, so I don't remember it precisely, and maybe at the beginning of tomorrow I can say what it is. It's not complicated. But it involves, the important thing is it involves things like 1 over p plus. So it can only be defined in light cone gauge. We assume p plus is non-zero. But for those states where p plus is non-zero, you can essentially solve the cohomology. Okay, so what we want to do is to compute scattering amplitudes. So we need the prescription. So the prescription obviously should be BRST invariant. And for tree amplitudes, I think Carlos already said what it is. It's just essentially we have 3 unintegrated and n minus 3 integrated. It's easy to show this is BRST invariant. It's not so easy to show that it's actually independent of which vertex operators are unintegrated. But that can be done. You have to use this property here to show that it doesn't depend on which vertex operators you choose to be unintegrated.
In the RNS, I mean, you could write down an expression which is where everything is unintegrated and you use the B goes.
That's what we'll do next. That's what I'll say. Okay, but this is at least the simplest way to compute it. And as I mentioned already, in order to define this zero mode, you have to have this funny measure factor. So now what we're going to do is we're going to introduce, or not introduce, but include the non-minimal fields. So, non-minimal fields, remember, are W bar, alpha bar. It's still left numbers. Okay, plus, okay, just to repeat, these are all left numbers. So the bar here does not mean that it's a right. These are these non-minimal fields. And of course the OPEs of them are trivial because it's still free field. So of course you can do the same thing here. Just to save space, I'm going to erase this. And we have to remember that lambda bar gamma m lambda bar is 0. And also R gamma m lambda bar is 0. So you've added 11 bosons and 11 fermions. And finally one has to modify Q. So Q is no longer lambda alpha d alpha. It's now lambda alpha d alpha plus lambda bar alpha. Okay, so this was necessary if we wanted to understand this zero mode measure factor is coming from a path rule. But now it turns out to be necessary for another reason, which is if we want to define a B-ghost, so as was already mentioned, an alternative way to compute is just you have B1 to Bn, and then you have n minus 3 B-ghost insertions. So, where these mu's signify Beltrami differentials, which you can either associate with the location of the vertex operators, in which case you return to this, or you can put them at other places, and then you have this formulation. Now this B, the only properties this B ghost has to have is that Q with B has to be equal to T. Where T is the stress tense, so in this case T is equal to P 1/2 dx dx plus P d theta plus W d lambda. And then if we have the non-minimal field, we also have W bar alpha d bar d lambda or alpha plus this. Okay, so these are the dependent variables. So let me just put closed here and you're finished. In this case, we don't have this variable, but of course we have Q and T, and we can ask if there's a composite object we can construct which satisfies this. Now, it will be useful to write this in manifestly supersymmetric form, which is 1/2 Im plus d alpha d theta alpha. Okay, so now we have a cohomology question. This object is obviously BRST closed because it's just a stress tensor and Q is conserved, so it's clear that Q of T is 0. And now the question is, can you write this as Q of something? What you find is that you can, but only if you allow objects which have 1 over lambda lambda bar dependence. So what does that mean? That means there's no globally defined object in pure spinor space. So globally defined means that on any patch of pure spinor space, so for example, I already erased the patches, but one patch would be where lambda plus is non-zero. Another patch would be where a different component of lambda is non-zero. This object B cannot be defined in such a way that it's well defined on all patches. For example, these vertex operators here are globally defined because they don't have any 1 over lambda. What you find is that this B ghost can only be defined if you allow it to have poles on certain patches. Let's just see why. So because Q has ghost number 1, it's clear that B has to have ghost number -1. Now the only object with ghost number -1 is W. W that sits here. But W is not gauge invariant. So it's clear that we need to have some other way of constructing ghost number -1 objects. The way to do that is to divide by lambda. So let's see what happens, what we can do to divide by lambda. So suppose we try to construct something, Q of it is going to be something like dx dx. Well, we have the D. So we have the OP here, that Q with D. There it is. Oh, here they are. This involves pi. So we can get pi of something as Q of something, but it's not pi, it's actually pi slash lambda. So suppose we consider this object here, lambda bar, pi slash D, over lambda bar. So the Q on the D is going to give you a pi slash lambda. Together this pi slash that will give you pi squared, which is what you want, times lambda bar over lambda bar. So that works fine. But the Q can also hit here, and of course it can also hit the lambda bars. So now we have, in addition to these, because Q is now non-minimal, we have additional terms. Q of lambda bar alpha, and Q of S alpha is equal to so when the Q hits the lambda bar, it will generate more terms. And also when the Q hits the D, it will generate more terms. Okay, what you find is that if you want to complete the procedure, you have to add more terms. So, for example, another term you have to add is then what you find is that in order to cancel the terms coming from Q of lambda bar, you have to start adding terms proportional to R. So I'm going to just write down terms and then I will explain how they can be simplified. In terms of this type. Furthermore, you also have these terms here, w bar d lambda bar plus sdr, which you have to generate. So these you can generate by just adding the term s d lambda bar. So you have a term here which has no poles. You have a term here which has a single pole. You have a term here, this would have a double pole. Turns out you have a term with a triple pole, which is proportional to this. And then finally you have a term with quartic pole, which has 3 R's and 2 N's. I'm not going to write that. And then it stops. So of course you can compute the coefficients of these terms. It's not so important. It is important, of course, you want to compute numbers, but the important feature is that it involves terms up to order 1 over lambda bar plus 4. The fact that it stops is actually an important statement, not about the cohomology of globally defined functions into a Spinor space, but if you allow things which have these poles, you can again compute the cohomology depending on the number of poles. And the fact that it stops is related to a cohomology question of an object with this number of poles. Okay, this is a slightly more condensed way to write the
And
details.
when you construct the vortex operators
Yes,
by studying dualistic modeling,
yes.
do you also allow for these kinds of poles?
Good. So I'll say a few words about that soon. Okay, so I can say it now. Okay, so in the original construction, we were looking for globally defined functions. We can ask, suppose we allow for functions which are not globally defined. So this is so there's an important obstacle.
Also, please note the gauge transformation parameters are not globally defined. You could get something in the cohomology from Q acting on some poles, which will now be declared to be not cohomologized, right?
Yeah, I think I'm about to clarify, but let me just ask again if I can clarify. So, suppose you allow functions with arbitrary number of poles. Let me prove to you that that is going to trivialize the cohomology. So consider this object here. So this object in the denominator is just equal to lambda bar L divided by Q. Lambda L. It's just Q of lambda bar gives you R, and Q of theta alpha gives you lambda. So this is just equal to this. Now suppose we take Q of this. Let's call this object psi. Q of psi is clearly equal to 1. Because Q on the denominator is 0, but Q on the numerator is equal to none. So once you have an object which satisfies Q on psi equals 1, then it means that any object which is annihilated by Q can be written as Q of C times V. So if you allow this state into your Hilbert space, the cohomology becomes trivial. So it's clear that we don't want, it doesn't make sense to try to compute the cohomology of all possible functions, including all possible poles. However, this object has the property that it has poles. Of course, you can expand this out, and because this object is nilpotent, R alpha theta alpha, psi starts out as lambda bar theta over lambda bar, but if you expand it out, the last term I determine the maximum number of poles. Will be this term here. So you will never get more than 11 poles just because r theta to the 11th is 0. But when multiplied by lambda. So this object has poles up to and including lambda lambda bar to the 11th. Now what you can consistently do is compute the cohomology allowing states which have poles up to order 10, but not up to order 11. If you allow poles up to order 11, the cohomology is trivial. If you allow poles up to order 10, then in fact the cohomology is the same as before. So these are the unique states in the cohomology if you only allow poles up to order 10. This is, of course, it goes number 1. It goes number -1. This is okay because it doesn't have any poles of order bigger than 4. So if you ask for the cohomology, it goes number -1, and you restrict to states with poles of less than or 10 or less, then this is the unique object. Okay, so so this is a complication in the theory which we will have to deal with later. But okay, is it at least clear what the definition
Lambda lambda bar to 4 11.
is? Say it again.
Lambda lambda bar to 4 11.
Yes, this is 11.
So in the correlator, the amplitude if some of these collides.
That's going to be the difficulty, yes. So as soon as if we have one B ghost, then we are fine. If we have two B ghosts, then we have poles of order 8. As soon as we have 3 B ghosts, well, it's a little bit better than that because actually this has a lambda bar in the numerator. So this actually goes like 1 over lambda bar to the cube. If you have 3 of them, you're still okay, you have 9. But if you go to 4, then you're stuck. So even if we're computing just tree amplitudes, but we use this parameterization, life is complicated. So, for example, you won't be able to compute, if you put in 4 B ghosts here, what you'll find is that when you try to compute the path integral, remember we were doing this Gaussian integration, we had to turn, so when we compute this, of course we have to put in the regulator. So maybe I should write that explicitly just so you don't forget. So this is object n here. Where n is equal to, the curly n is equal to this Gaussian cutoff. So we're trying to compute d11. We have a term e to the minus lambda bar cosine theta. This is what we're trying. And then we have these terms. Okay, lambda a is a n. So if you have n external states. But now you're going to have these b ghosts, which will have 1 over lambda bar cubed. And let's suppose you have more than 11. Let's suppose you have 12 of them. Well, this Gaussian is, of course, well defined when lambda goes to infinity. So if you didn't have this term, the integral would be well defined. But because when lambda goes to 0, this goes like lambda to the 11th, or lambda squared to the 11th, you have a divergence when lambda goes to 0. So that's another way to see why there are problems when you have more than poles of order 11 or long or more. Because now the path integral is no longer well defined. U lambda equals 0. Okay, so this is a complication. I don't think this complication has been, there are proposals for how to treat this complication, but none of the proposals have been used to do explicit computations.
But already at genus 2 you need more vehicles, right?
Genus 3. So genus 2 you just have 3 vehicles. It's 3g minus 3.
You have left and right.
Yeah. At genus 3, that's where you run into possible problems.
So how was the calculation done in this?
So Carlos would maybe do this in the last lecture, but he just looked at the low energy limit. And in the low energy limit, you can show that these terms in the vigos don't contribute. So he only used these terms in the vigos, which don't give rise to the problematic poles.
So that computation doesn't compute the full.
So computing the full 4-point amplitude is, I don't think it's possible unless one figure out, well, there are proposals, so not possible is true, but there has to be progress on using these proposals. It's not straightforward.
So at genus 4 onward, even the low energy limit is problematic or?
No, so it depends on which computations you're doing. So, for example, there are certain vanishing theorems you can prove, which, for example, it's easy to show that these terms don't contribute.
When?
Which vanishing theorem?
No, when? Under what condition?
So, for example, suppose you want to compute a 3-point amplitude at high G's, 3-point massless. That's easy to show that the amplitude vanishes.
All loops, all genus.
Yes. So, it just comes from zero mode counting. And it turns out, I'll try to say this, maybe I'll say it today, maybe I'll say it tomorrow. But in order to get a non-vanishing answer, you have these fermionic variables, the p's and the thetas. In order for the amplitude to be non-vanishing, you have to have a certain number of zero modes. So it turns out the regulator can give a certain amount of zero modes, but you also need to get zero modes from the vigos. And if the zero modes from the vigos just come from these d's. So these terms essentially don't contribute for those d modes. So you have to be careful, but it's that kind of argument. If you can argue that the fermionic zero modes force the thing to vanish, then you're okay.
So for example, for the genus 4 up to the 4 amplitude, 4 graviton, does this last term contribute or not?
I think so. So I don't know, but let me give you the reason why I said I think so without any explanation, which is there are terms in the effective action which are F terms and terms which are D terms. So terms which are protected by supersymmetry and ones which are not. And I suspect this. These terms, the complicated nature of these computations become relevant when you're trying to compute D terms. And I think the for loop is already a D term. So that's my naive guess, but it's just a naive guess. So in fact, you can prove that F terms never require the complicated regulator. So if you're computing an F term, it's not difficult to prove that that you never get poles of order greater than 11. So an F term means that the vertex operators contribute fewer than the 32 thetas. But as soon as you have a D term, which the vertex operators have to contribute 32 thetas, the regulator you may need to deal with this complicated question. So
in this language, will genus 0 endpoint function be F term?
Okay, so what I said is that it's necessary,
Yeah,
but it's not sufficient. So for the tree amplitude, certainly for this one, you don't need the complicated regulator.
But if the number of B insertions is more than say 3, then it will have a problem.
Yes, but I don't need to. So yeah, tree amplitude.
But suppose you do start with that multiple insertions or something.
Yes.
You do similar to what one does for RS.
Yes.
And then you are saying that somehow this all this lambda about denominator should cancel.
Yes. So when you say it will cancel, of course it must cancel because the two are supposed to be equivalent.
Yeah.
But it will cancel only after dropping surface terms. So these two, the first line and the second line are only equivalent up to surface terms.
Yeah. And they will cancel presumably up to, only if you regularize. Otherwise like 0 times.
So you'll have to put in a regulator and Well, again, nobody has, because the proposals for regulators are not practical in the sense that I don't know how to explicitly compute with them. I wouldn't even know how to check this, but
Oh, so wherever you can use this, I mean, decide, I mean, without hitting this lambda lambda to the power 12 in the denominator, explicit computation has been done to check that this expression for B gives the right result?
yes. So, for example, the most detailed one is Carlos and Umberto. They did 3 loop and what we assume is the correct result they found. Of course, nobody's done the RNS computation, but they used SQL to argue that they got the correct result.
And for the 3 amplitudes, you were saying that you get these 2 expressions that same up to surface terms.
Well, that I can argue without doing the computation. It's just I use the fact that Beltrami differentials as a gauging variance associated with the choice of the Beltrami differentials. So
you just convert the B's to U's.
convert
The fixed vertex operators to U's, integrated vertex.
right. But if you ask me to do the computation of the second line, I wouldn't know how to do it for generic positions of the B's. It's something that needs to be understood better.
But is it possible to study this degeneration limit without using integrated vertex operator? So if I want to study the degeneration limits, even for the tree level, so usually say like it's better to use the unintegrated form.
The unintegrated. So yeah, that's the second line. Yes.
So then we have this B system.
Yeah. So that's problematic.
So even at the tree level, it looks.
Even at the tree level, it's problematic. Yeah. So we don't. It's something for you guys to solve. The answer is no. It's not that you don't know the answer. It's that the procedure for working with these, when you have many poles. So let me tell you why I am optimistic it can be done. Okay? So let me tell you, and all of these proposals, not all of them, I think it's just, I know my proposal, I don't, which was done with Nikita Nekrasov. There may be other proposals, but they all use the fact that the B's are not all at the same point. So although they all have this kind of pole dependence, the problem is really only important when all of the poles are at the same point on the world sheet. In this case, they are not. So in some sense, you can do the part of the computation on one part of the world sheet, do another part on the other part of the world sheet, and then solve them together. So I would say, in principle, it must be possible to do this. I just don't know in practice how to. Any other question? There's another way to say it, which I have not had the. If you take the OPE of 2 B ghosts, you get something with more poles, right? But as I told you, the cohomology tells you that this is a unique stated ghost number -1, and there's probably a unique stated ghost number -2 also, which doesn't have lambda back to the -8. So probably there's a BRST trivial transformation you can make which can reduce the number of poles. So that's something that also could be factored.
Talking by the same argument that you gave here, that if you have some r theta to the 10, that OP in the numerator will vanish. There is an r in the.
Well, but these have D's. It's not quite. So, and this doesn't have any. So, well, it has 3 R's, but I think you'll have to add some BRST to drop these terms. So it's something to be explored. I mean, I don't.
Hasn't this computation been already done? That b squared equals 0?
Okay, sorry. I don't want them to be at the same point. Or I want the 0. So it's true. By dz limit y goes to z. It's 0 as in bosonic string theory. But there's a term which goes like y minus z times something. Let's call it B2. This is the object which I need to compute.
So that's like B del B.
Right.
There is no hope that there is an extended formalism which will be fundamental and this will have emerged by eliminating maybe some fields.
Yeah, I guess it depends on what your hope is. So you're trying to give a proposal for how to eliminate. It's like some auxiliary field that when you integrate it out, it gives you a pole.
Something like that, yeah.
Maybe. So, I haven't had any good ideas, but I don't think there have been that many people thinking about it. Okay, so this is an open problem, an important open problem. So RNS has also many open problems. But at least, we can compute tree and loop, and I can show to you vanishing theorem. So let me sketch how to, for example, do the one loop and show that even two loop, how to show that the amplitude vanishes when you have less than 4 external states. So of course that can be done in RNS, but it's a horrible mess. Beautiful mess if you want. Who's doing the computation. Here I can do it in a few lines. And it's of course because supersymmetry is manifold. Okay, so let me do it. So the
And
only
this is specifically designed for flat space. I mean, if you want to do Calabi-Yau, you have to go to use a different formalism.
Okay, let me say a few things about curved backgrounds later, but you can of course do this in any background which is a solution of supergravity equations of motion. But as in Green-Schwarz, you have 16 thetas. Okay, so Calabi-Yaus don't have n equals 4 supersymmetry, they just have n equals 1. So you would prefer to work with a formalism which have 4 thetas and maybe 6 psi's like in Calabi-Yau. So that's the hybrid formalism. Okay? But if you work in this approach, as in Green-Schwarz, the signal model does not decouple into a 4-dimensional piece and a 6-dimensional piece. So it's not the sum of 2 terms, as it is in RNS. So that's an inconvenient feature. Although there are some special things that happen with Calabi-Yau, I can say, let me say another thing. There certainly are simplifications that happen with Calabi-Yau. Nobody has explored this yet in Twistors. Not nobody. There was a paper by Bruno Valillo and Osvaldo Changier, but certainly computing amplitudes, I think there are things that can be done with Calabi-Yau using this. But they haven't been done yet. But I think that was what you were pointing out, that the thing doesn't factorize, is that?
Yeah. Nevertheless, I mean, as long as it's possible to use the CFT data, I mean, if you have to start doing calculations on Calabi-Yau, it will be hard, right? But Calabi-Yau, suppose that is CFT, and you know how to calculate potential function.
Right. So, but this doesn't factorize into the sum of 2 CFTs. But certainly there's something that can be done. Nobody has done it. Okay, so let me say something about how to do computations for loops. So there's one more feature we need, which is this regulator is good enough for tree amplitudes. But for loop amplitudes, we also have an integration over the W's. Because the W's, remember, are conformal weight 1. So on a genus G surface, they have 11 G zero modes. So now we need a regulator not just for the integrations over the 0 modes of lambda. Those don't change for genus G because it's conformal weight 0. We now have to regularize the W's and W bars. So that can be done in a simple way. I'll introduce this problem. Okay, what do these I? So W on a genus G surface has G zero modes. So let me label these zero modes with capital I. And now you can use the fact that this object here is Q of Wi alpha SIF. So using these transformations of Q of S and Q of W, you find that this is 1 plus something VRST trivial. So this one was Q of I multiplied alpha. Okay, so the regulator for genus G zero modes is essentially the same form as the tree level. And it's important to see that this involves the fermionic zero modes, just like this does. So just like this term here reduces the number of thetas from 16 to 5, this reduces the number of zero modes of D from 16G to 5G. So when one does the computation, which means integrating out all of the D's and all of the thetas, so with these regulators now you have N, they're all integrated. Let's do, at one look, one of them is unintegrated and the other N minus 1 integrated. But if you're doing G different from 1, then they're all integrated. And then you have B, 3G minus 2. So this is the type of computation we're going to have to do at genus G. And as I mentioned, this N can give you 11G Ds, and it can give you 11 thetas. So the other
N is what? N is that regulator?
N is this regulator here. So now the product of these two. And of course it also gives you 11 R's and 11G S's. So the remaining 5 GDs and 5 thetas have to come from either the vertex operators or the B ghosts. Now the B ghost can at most give you 2 Ds. There's no terms of the B ghost with more than 2 Ds. So let's look, for example, at 2 loop. There's 3 B ghosts, so that can give you 6 Ds. So 2 loop is 22. This is 22. Okay, 22 plus 6 gives 28, but you need 32. So we're missing 4 Ds, and these have to come from the vertex operator. So each vertex operator can contribute at most 1 D. So if you have fewer than 4 vertex operators, the amplitude vanishes just because of zero mode count. Okay, so that's a nice vanishing.
At this stage, you have not used these are massive ones.
Yes, so if they're massive, then they can have, so I didn't even tell you what the massive vertex operators look like, but the massive vertex operators have the integrated ones, or let's do the unintegrated one. The unintegrated ones for massive will involve derivatives of these, and not just zero modes. So for example, the unintegrated one, you might have a term like this. So this would be a possible term in the first massive level. So it means that the conformal weight of the, of course you get conformal weight from the mass squared, and the contribution from the mass squared is negative, so that has to cancel the conformal weight coming from the other variables. So the first massive level, these have to contribute conformal weight 1. So there's a term which is proportional to D. And when you look at the integrated vertex operator, the integrated one would have a term with 2 D's. So there would be a term DD times, it would be some superfield here. So this would be an allowed component of the massive vertex operator. So the fact that only 1 D comes from the vertex operator is special to the fact that it's massive. So if it was massive, you could get more D's.
So, this part also, B to the power 3D minus C, that will contribute 6 D. It should contribute.
Okay, so each B, so G is equal to 2,
Oh, G,
so this gives you BQ.
And those U1 to UN coming from?
So these are the n external vertex operator. So we're doing endpoint scattering.
Are we going from the second line on top?
No, now we're doing the first line. So we're not doing tree amplitude, now we're doing, so with tree amplitude, look, any U can be exchanged for a V and a D. But I want to reduce the number of V's so I won't have all my vertex operators be integrated. Okay, any other questions?
So K you define somewhere? K alpha beta?
I'm sorry?
K alpha beta you define somewhere?
I didn't hear the first thing you said.
K alpha beta you define?
K alpha. This K alpha is supposed to be a superfield, like this kind of superfield. I'm just trying to say that there's fields here. Okay, so for amplitudes, Carlos, is there something else I should say? I don't know how much you're going to say.
Me neither.
Okay. So I think it's clear what the open question is. It's how to deal with the amplitude when you have more than 3 B ghosts. For tree amplitudes, okay, there's another thing I can say, which is this is supposed to be equal, of course, to RNS amplitude, at least when the states are never short. So I think, well, maybe it was obvious, but I should say that well-known scattering in RNS is a mess. Okay, so the first computation of four fermion scattering in RNS was I don't know how to describe it. It was a great achievement at the time. It was, I think there were 3 groups that finally found the 4-point fermion amplitude in RNS. Then after Fiden, Martin, and Schenker, okay, it became more or less easy to do, but 6 fermions in RNS now became a big challenge, and I think that's the furthest that's been done for RNS, at least in covariant notation, so writing it down in terms of gamma ray. Whereas in this language, you can do easily n fermions just because everything is in superspace, so you just keep all the thetas and just in the end you use Gauss's procedure for getting the fermion scattering. Okay, so, but for never short scattering, of course, RNS is not so bad. I mean, so how does this compare? So, in order to show equivalence for tree amplitude, the easiest way to do it is for the massive states, is you use the fact that the vertex operator, or the integrated vertex operator, is very similar to the vertex operator in RNS form. So remember, in RNS form, the integrated vertex operators of this form, where AM is the gluon vertex operator. Now if you look at this and expand it in terms of theta, you find in terms of your lowest order in theta is just in the gauge that Carlos was discussing, is just dxm am. Now instead of psi, you get mmn plus 1/2 p gamma m theta times dmam. As I already already mentioned, the level of this is the same as the level of that. So using this construction, it turns out the terms which are higher order in theta here never contribute for another short scattering. So plus dot dot dot. Plus order theta squared. These terms never contribute, and so it's relatively straightforward to show that the gluon scattering is the same. But what about massive states? What about fermion scattering? Nobody has been able to prove that the two amplitudes are the same. So we don't have an equivalence proof for these scattering amplitudes, even tree amplitudes. For
I guess for NS, by factorization you can argue for.
So again, any product of massive states can give a massive state, so that's right. So using OPEs of that, you can argue that they're the same. But what about loops? Okay, at one loop, in RNS you have to sum over spin structures, and here you don't, and I can't prove that they're equal. So that's a mystery. So certainly it's something that if somebody figures out a way to prove that they're equal, that would be very important. They may have
One thing one can try to do is this spinor of isophotic heterotic, right? Because that the spinor state of isophotic heterotic,
yes.
that doesn't appear in the intermediate state because it's
Okay.
all the massless states are vectors, right? So
Okay.
in principle that could be different in pure spinor and this one and the RNS.
You mean the vertex operator or the amplitude?
Amplitude. Because it doesn't factor in the massless state amplitude doesn't factorize on that.
Okay, good. So there's a paper. So somebody should look at that. And obviously, the proof will not be simple just because, as I mentioned, we don't know how to compute it when the B ghosts are separated from the vertex operator. So even for tree amplitudes, the things we can do in RNS in a simple way that we can't do in a simple way here, and vice versa. So fermion scattering here is essentially straightforward, but in RNS, okay, we know that there are complications. So you would learn a lot if you could.
For massive states, the integrated vertex operators are easy to write down.
No, it depends what you mean easy. So you can it was worked out the first massive level.
But is there a systematic procedure that one follows?
Okay, let's say in RNS, is there a systematic procedure? What would you say is the systematic procedure?
So you look for primaries, right?
Yeah, but how do you look for them? Is there a systematic procedure?
You just apply ln.
Yeah, you
And-
solve
yeah.
the same here. So you have V, and you require the Q to be equal 0, and you define V up to Q of something, and then you have to solve these equations. So in that sense, it's systematic, but solving these equations is not so straightforward. I mean, these give superspace equations.
For the integrated ones, it's not Q be equal to 0, right? You have to first find V and then you calculate, solve that second one, is it?
Yes. You can, of course, do it the other way around. You can look for conform weight one object, which satisfies the property that Q of U is D of something. Yeah, so these are superspace equations, and it's easy to find the superspace equations. So that part is easy. The difficult part is solving the superspace equations.
But suppose one finds Q,
Yes.
then one can get V by taking the OP with B. I mean, is that a systematic procedure?
Then I can take V by what?
Taking OP or B with U. Suppose we just,
Suppose somebody gives you what U is. So U is the massive one. That's what you're saying?
yeah. Take that.
Okay. Yes.
No, not V. I'm saying V. V is unintegrated one, right?
So V
This is
massive.
easier.
If somebody gives you V massive,
Yeah.
yes.
B times
Then can you just take V times V massive and get U? Because in RNS,
V massive times U massless, is that what you're saying?
No.
B
B,
fit.
B.
the V goes.
B goes.
The B goes. You get it up to cohomology. So yes, but for example, let's do it here, just a good example. So let's just take B times U. Well, B has all these poles in it.
B times V, I think.
B times C.
B times U.
No,
U is
so U is
controlled.
unbounded. Yeah.
Oh, yeah, sorry.
Yeah, B is unbounded.
So this will have lots of poles, but if you add something BRC trivial, you can get rid of the poles, and this will be good. And in fact, it's not easy.
There is no analog of separating matter from the ghost. I mean, in RNAs, one of the advantages is that you can just look in the matter sector, classify primaries, and then multiply by C. There is no analog of that statement here.
No. So the B goes, because it's not a fundamental field, there's no sense in which this goes.
Starting from DDF operators, can one give rotations and symmetry transformations to construct covariant operators?
Okay, so there is a gauging which just reduces to the DDF operator, that's what you're asking. So by finding the
So DDF operators are constructed.
yes.
Then can one give rotations and other symmetry transformations to construct? The problem with those operators is that they are not covariant.
That's right.
Yeah. So can one get, with the help of the equations that to be solved, the DLS equation and those operators, can one construct covariant one or guess something?
Yeah, in principle, yes, but it's just because it's more complicated because you have spinors. So in RNS, it's essentially straightforward. You just take a light cone vector and say, okay, now it's not light cone, it has 2 extra components. But when you have spinors, it's more complicated because you're missing half of the spinor. So in principle, yes, but in practice, it might be complicated. Yeah, so all of these questions are good questions. This one, for example, I can tell you what this lambda is, at least for the masters. It's not complicated. So I suspect there are nice answers to this, but okay, up to now, it's just by doing these computations that you see that things are working. So this is open string, of course, closed string, you take the left-right product. So that part is straightforward.
So, just one more. The way that you found B was that demanding that anti-commutator, you would give me the natural contents of P. So is this construction unique?
No. So you can add B, anything BRC trivial,
Okay.
but up to something with BRC trivial, yes, it's unique.
But you cannot get rid of that term.
The four is stuff.
No. And in fact, one can show that the presence of this term is related to a cohomology. So, in fact, you need this term. Instead of constructing the B goes starting from here, actually the correct way to do it is starting from here. You look at the cohomology not of lambda alpha d alpha, but you look at the cohomology of this other term, W bar R. And that has this term, it's cohomology, and then you go back.
Back on the P equals
Yeah. Okay, so this is something fundamental, but obviously it doesn't mean that it can't be understood there. Okay, so I have 5 minutes. There are different things I can do. I can sketch. So what are the things that people want me to do tomorrow? Just so I can talk about twistors, I can talk about ADS5, I can talk about I guess those are the 2 choices.
Twistors?
You could talk about,
Okay.
you can talk about both also.
Yeah, sorry?
You can talk about both also.
Yeah, but half each. So let me say a few words about, I have 5 minutes, let me say something about curved backbones, and then I'll start with twistors tomorrow, and if I have time, I can say something about ADS5. I mean, I think ADS5 is probably the area that the most, how can I say, the most potential is there for making progress with, because there's a huge community of wanting to do things with ADS5 times S5, and they can't do it using green shorts. So, but, okay, you need to develop something that hasn't been developed. But I think there's a lot that can be done. Okay, so let me say a few things about curved backgrounds, and then tomorrow I'll start with this. So this action here, if you want In curved background, of course, you take the left-right product to construct the closed vertex operator. But you close it, you're going to have the following form. So these two terms together, as I already mentioned, can be written in the form AM DZM, where capital Z is either X or theta. So when you take the left-right product, these combine to two terms, either symmetric, or graded symmetric, or graded antisymmetric. So that comes from the left-right product of this with itself. And now you can get the left-right product of this with this, etc. So those are kind of interesting. You get a term of the form d alpha d bar of dm. And this couples to something with a spinor index and a superspace index. And then, of course, you get the complex content. And then you can also have this with this. So I'll write this as omega alpha AB. So of course all the objects I write down have conformal weight 1, 1. Then you're going to get a term R, A, B, C, D. So that comes from the left-right product with two of these. And I forgot another term, which is W, L bar. So these are, of course, come from the covariantization of the W d bar lambda. And from the covariantization of the P d bar theta, you have the term d alpha. Sorry, that's already done. That's these terms. Okay, so in a flat background, this term becomes d alpha d bar theta. Now there's one other term which is interesting, which is you have d with d bar. So of course this term is the same as Green-Schwarz. Just because this term, I mean the first, well, this thing here squared is the same as Green-Schwarz. The new features come from here and here. So all of these other terms are not in the Green-Schwarz sigma model, but they're needed in this sigma model for BRST invariance. So BRST invariance is essentially replacing kappa symmetry in Green-Schwarz. And you see some things which are interesting. First of all, these terms are just the curved space version of d bar theta. These terms play the role of connections. So they're anything involving n or n bar are like connections in the curved background. So these are indices in SO91. And finally you have a term which looks like the curvature. So this is it's the analog in RNS of the term coupling psi left squared with psi right squared. So the final term here, constructed out of d and d hat, couples to a field strength whose lowest component is the Ramon-Ramon field strength. So this F alpha beta, the lowest component of it, means the component when theta equals 0, is just the Ramon-Ramon bispinor field strength.
This n is only the ghost part, right?
N is the same as it was in flatback. I'm just W gamma n lambda. But as conformal weight 1 is 1 0, only 0 1.
That's only the ghost part of the Lorentz generator, is it? Right?
Say it again?
There is a ghost part of the Lorentz generator, isn't that right?
That's right. So the magic part of the Lorentz generator is already included in these terms. So just as when you write down in RNS, there's a coupling of so this is the coupling of the curvature to the non-x part of the Lorentz generator. Okay, now the nice thing is that when you're working in Ramon backgrounds where this field strength is invertible, you can actually treat D as an auxiliary variable, because this means that D can be integrated out. So in the ADS5 times S5 background, which is just the sigma model here where these background fields just take the values of ADS5 times S5, F alpha beta is just equal to
What is the delete on this?
oh, thank you. Okay, so of course if you look at the closed vertex operator, you don't see directly the dilettante. So the sigma model is not quite this. So the sigma model is equal to d squared z 1 over alpha prime times this, plus another term, which is just the usual d squared z two-dimensional curvature times the dilettante. So, as in bosonic string theory, the dilettante couples higher order in alpha prime. Okay, so in the ADS5 times S5 background, F alpha beta is just equal to gamma 0, 1, 2, 3, 4 alpha beta, which is of course invertible. So the inverse is just the same matrix. Okay, times n, where n is the field strength, the flux of the field strength. Okay, so in that background you can actually integrate out d alpha and get an expression which only depends on x and theta hat. It's not the Green-Schwarz action. The Green-Schwarz action is this. But it has BRST symmetry, and in fact it has a propagator for the fermions which you can invert. So you can quantize. Okay, so let me just I'll just write the action now.
You said the d alpha can be integrated out. Is it completing the square or that?
Because this term is invertible, F alpha beta is invertible in ADS5 times S5. That means the equation of motion for D is just an auxiliary equation of motion. So after integrating it out, you just take if you've never seen the cycling ADS5 times S5 action, you won't understand this, but if you have seen it, then so the cycling action is built out of a coset of PSU224 form, and there are essentially two terms. There's a term which is so it has a term this A is a vector index, so it's antisymmetric in Z and Z bar. Now when you do the construction here, you find that it's not antisymmetric. There's a symmetric part. So I don't remember the factors, but it's something like -1/4 instead of it's not antisymmetric in Z and Z bar, because when you integrate out D and D hat, you get the contribution to this, which is no longer antisymmetric in Z and Z bar. So because it's not antisymmetric, you can invert the propagator.
This is mid-side cycling.
But side cycling is with the minus. So it's, the fermionic part is antisymmetric in Z and Z bar.
But you have one foot in this case.
That's right. These are the different coefficients. So to see that the antisymmetric one, you can't define the propagators. If you go to linearized level, antisymmetric means d theta, d bar theta bar, minus d bar theta, t theta bar. To linearize, so just to keep the quadratic term, but this vanishes when you're fermionic. I don't know if I did it right. Right, because you integrate by parts here, and you'll get the same term.
Sorry, this is delta alpha beta or epsilon alpha beta?
Okay, this delta, sorry, I didn't tell you what delta is. Delta alpha beta is just this. So F alpha beta.
Okay.
It's just the gamma phi. So it's antisymmetric in Z and Z bar. But these are fermionic, so it makes sense. But the point is that the quadratic, the term which is quadratic, theta is it's a surface term. Whereas if you change the coefficient, of course, you're left with something which survives. So you can just define the propagator. Okay, so in any case, that's, and of course, they're extra ghosts, so this term also survives. So the action is related to the Green-Schwarz and the Zeichen action, but it's slightly different. And these differences allow you to, for example, check that it's a conformal field theory. You can also start to, there are various properties of this action that are interesting to explore, like if there are non-local conserved currents, so you can do all that using this action. And in some sense, it's much more straightforward because you don't have to fix kappa symmetry in order to do the computation. Okay, so that's where I'll stop today.